Let's use derivatives from calculus to find global extreme values of functions. Number 1, find the global maximum and minimum values, also called absolute maximum and minimum values. Those are the outputs. Whenever I use the word values, I mean outputs. And where they occur, that means the x-coordinates of those points. In this case, the function is f of x equals x cubed minus 3x squared plus 20 a cubic. The interval that we are optimizing this function over, the domain that we're considering, is this particular domain. I just happen to pick it because it works out nice for the example. X goes between -2 and 5/2, including the endpoints. That's called a closed and bounded interval. And there's a theorem called the extreme value theorem that guarantees, if your function is nice, continuous in this case, and the interval in question is closed and bounded. Closed means include the endpoints, bounded means it doesn't go off to infinity. Then there will be extreme values, global extreme values. It also turns out that those values occur either at the critical points of the function or at the endpoints of the interval. We're also going to graph the function to illustrate the answers and find the best possible bounds for the function over the interval that's related to the global max and min values. So we start with the derivative. F prime of x, take the derivative of a cubic, you're going to get a quadratic, is 3x squared minus 6x plus 0. For the critical points, we want to set this equal to 0 and solve for x. In general, with a quadratic, you might have to use the quadratic formula, but here it's very easy to factor this. You can factor out a 3x out of both terms, and you're left inside with the parentheses here of x minus 2. That's equal to 0. That gives critical points at the values of x that makes these factors 0, x equals 0, and x equals 2. You should double check that both of those critical points are in the closed interval. Are they both between -2 and 5/2? Yes, they are. 5/2 is 2.5. So these are in the interval. If they're not in the interval, then you ignore them. As in the previous video, we focused on local maxima and minima, and we used the first and second derivative test to test those. But actually, with global extreme values over closed and bounded intervals, it's easier. You don't need to think about derivative tests. You just plug in the critical points of the function and also the endpoints of the interval. So we'll start with the leftmost endpoint, -2. Plug that into the function. We're going to get -2 cubed minus 3 times -2 squared plus 20. We will check our answers, by the way, with technology here. -2 cubed is -8. -2 squared is +4 times -3 is -12. And then add 20. And lo and behold, you get 0 here. That is the value of the function at -2. What's the value of the function at the critical point 0? F of 0 is very easy to find out. That's 20. At the next critical point 2, f of 2 is 2 cubed, which is 8, minus 3 times 2 squared, which is -12, and then plus 20. So we have 8 minus 12 plus 20. -4 plus 20 is going to be +16. And finally, we check the right endpoint, 5/2. I'm just going to go ahead and use my calculator here for that one to make it quicker. That's f of 2.5. So we need to plug in that number, 2.5, into the function. Cube it, subtract 3 times 2.5 squared, and then add 20. Looks like we get 16.875. Now look at these outputs. What are the outputs? They are 0, 20, 16, and 16.875. Whichever one is biggest is the global maximum value, and whichever one is smallest is the global minimum value. 20 is the biggest one. That is the global max value. And it occurs at x equals 0, right? Value means output. We're looking at the outputs of the function. That's the biggest possible output in this interval. It occurs at x equals 0. And the smallest number here is 0. That's the global min value. And it occurs at -2. The global max occurs at a critical point in the interior of the interval, and the global min occurs at the left end point of the interval. You can graph this function without technology pretty easily. It's cubic. You should be familiar with the graph of a cubic. It does have a vertical intercept of 20. We know the value f of 0 is 20, is the global max value on this interval from -2 to +5/2, 2.5. That's up at 20. The global min is at -2 is 0. If this is going to be a global max value, and if it's occurring at the interior critical point here, it will also be a local max value. So the graph will have to look like this. And we know with cubics, they're going to come back up again. F of 2 is not much lower than 20, it's 16. And F of 2.5 is slightly higher at 16.875. So over this interval, the graph looks like this. If you kept graphing it further, you'd go up this way. There'd be, over the entire real number line, the graph goes up forever and ever as x goes to infinity, and it would go down forever and ever as x goes to minus infinity. Let's just double check this with a calculator now. So go to my y equals screen, plug in this function, x cubed minus 3x squared plus 20. I want to pick a window that will look something like what we see here. Let's certainly make the x min and x max be the left and right endpoints of the interval. And let's go from -5 to, say, 25 for y. And here's the graph. Yep, looks pretty good. Global min of 0, min value of 0 occurs at the left endpoint, x equals -2. Global max value of 20 occurs at the interior critical point, x equals 0. Yeah, but the fact that I stopped the right endpoint at 5 halves means this point is not a global max value. If I made it further to the right, like maybe 3 or 4, this would go up high enough that over such an interval, the global max would occur at the right endpoint. What are the best possible bounds for this function? By best possible bounds, we mean best upper bound and best lower bound. What is the smallest possible value of y that is always above the output of this function over this interval? Well, that's the same as the global max value, 20. And what is the largest possible value of y that is underneath the graph for all values of x in this interval? That occurs at y equals 0. So the global max value is also the best upper bound, and the global min value is the best lower bound. If we want to be a bit more precise about what that means, we can say these things imply that the outputs of this function are between 0 and 20 for all x in the interval from -2 to 5 halves. And those are the best possible bounds because the function actually does attain those values as well. In problem 2, we do the same kinds of things, but now the function is f of x equals x times e to the -x squared over 2. And you can see then when we find the derivative, we'll need the product rule, and we'll also need the chain rule. But the rest of the directions are similar. We once again have a closed and bounded interval. This time I picked -2 to +2. We're going to graph the function. We're going to think about what the best possible bounds of the function are over this interval. So start with the derivative. F prime of x. By the product rule first, there's the first function x, there's the second function e to the -x squared over 2. Maybe you prefer left and right functions. The derivative of the first function x is 1. The derivative times the second function e to the -x squared over 2, plus the first function times the derivative of the second. Or overall, you could do right d left plus left d right, if you like it that way. So we have the derivative of e to the -x squared over 2. That's itself times, by the chain rule, the derivative of -x squared over 2. Bring down the 2, subtract 1 from the exponent, cancel the 2's, you'll get -x. We want to set this equal to 0 and solve for x. Remember to factor out whatever you can factor out. That's always a good idea. And then look at this expression. You see e to a power which is never ever 0. So the only way this is going to be 0 is if this is 0, which pretty clearly is 0 just when x equals plus or minus 1. Those are going to be the critical points. X equals plus or minus 1. If you want to factor it, you can do that as well. It's 1 minus x times 1 plus x to see that. Always remember, are these critical points in the interval in question? The answer is yes, they are. But it's possible I could have chosen a different interval and they may or may not have been in that different interval. So you always need to check that. And again, just like in the first problem, we don't need to use the first or second derivative tests here. Those are for local extrema. It's not that we couldn't, but if you're just after global extrema, you can just check the value of the function at the endpoints and at the critical points. f of negative 2, replace x with negative 2 in the original function, not the derivative, not the second derivative. In that original function, I'll get negative 2 e to the negative 2 squared is positive 4 over 2 is 2, but then I have a negative sign there. So that's going to be negative 2 power. Let's go ahead and approximate that right away. By the way, this function is an odd function, and so once I find the first two, I can easily find the second two. Negative 2 times e to the negative 2 power is approximately negative 0.27. F of negative 1, replace x with negative 1, you'll get negative 1, or just negative sign, e to the negative 1/2. E to the negative 0.5, but with a minus sign, that's about negative 0.61. And yeah, this is an odd function. It's got origin symmetry. F of negative x is negative x e to the negative, careful, negative x squared over 2. But that negative x squared is the same as x squared. This is the opposite of the original function value at x. That means it's an odd function. That means the value of f of 1 is going to be the opposite of the value of f of negative 1, which we could also easily find out just by plugging the numbers in, of course, but I wanted to emphasize that that is helpful sometimes. And f of 2 will be the opposite of f of negative 2. So this one's about positive 0.61, and this one's about positive 0.27. The global min value is this number exactly, which is approximately that number. That's the global min value. It's also the same as the best lower bound. I'm answering both questions at once here. You could think of it as a y value corresponding to a horizontal line, like we did with the first problem, that is underneath the graph over the entire interval, and in fact it's the highest possible such horizontal line. The global max value is right here. And by the way, that's a maximum. The global min value occurs at x equals negative 1, and the global max value occurs at x equals positive 1. Global max value, it's also the best upper bound. Thinking of it as a y value and thinking of it as graphing a horizontal line at that value of y, it's the lowest possible horizontal line that is above the graph over the entire interval. Now let's go ahead and graph it. We can graph it pretty easily without technology here, though it's not going to be super precise as far as plotting points. Do notice also f of 0 is 0, which it would have to be since it's an odd function. I'm graphing it over the interval from negative 2 to 2. Negative 0.27 is the value at negative 2. Global min is at negative 1. So it's got to go down. That global min also would have to be a local min if you did use the first derivative test. Let's make it a bit more like this. If you did use the first derivative test or second derivative test, you could confirm it's also a local minimum. And then it's got to do something like this. Again, it's an odd function. If 1 is about there, I guess it's got to go a little higher over here before coming down like that. Okay, so approximately like that. Not worried too much about getting the concavity right. It's possible it changes from concave down to concave up over here. I think it probably does. But let's not really worry about that. Let's go ahead and use the calculator now to confirm this seems approximately right. X times e to the negative x squared all over 2. Window, x goes from negative 2 to 2. Y min, say negative 1. Y max, positive 1. Y scale, 0.1. And we get a graph that matches what we got pretty well. Not sure, but I think maybe at x equals plus or minus 2, there's an inflection point. So if I graphed it over a bigger interval, the graph would be concave up over here and concave down over here. But I'd have to find the second derivative to test that. For number 3, the function involves a cube root. So it's a little strange. Something a little funny happens with this example. The interval in question, once again, is a closed and bounded interval from negative 1 to 8. By the way, in our very last problem, which is an application, we're not going to have a closed and bounded interval, but we'll still think about global max and min values. Once again, same directions. Find the global max and min values where they occur, graph the function to illustrate your answers. What are the best possible bounds for this function over the interval? By the way, in the previous problem, I should have probably drawn horizontal lines at the best possible bounds. All right, so take the derivative. You have to be careful. The derivative is actually undefined at x equals 0. The cube root of x, of course, is the same as x to the 1/3 power. That is a power function. If you bring down the 1/3 and multiply by 3, you get 1. And subtract 1 from the exponent, this is x to the negative 2/3 power. And then minus the derivative of x is minus 1. This is the same as, by definition of negative power, 1 over x to the positive 2/3 power minus 1. Now careful, the fact that this is undefined at 0 is not really a proof that f prime of 0 does not exist. To really prove f prime of 0 does not exist, you'd really need to go back to the limit definition of the derivative. It is possible to do. It's an indication that it might be not differentiable at 0, and that is true. Though the way it's not differentiable is a little weird, as we'll see when we draw the graph. Once again, set this equal to 0 and solve for x to find critical points. There is also, because the derivative at 0 is undefined, a critical point at 0. I'll write that down here after I solve for when this is 0. That's easier to solve for x than it might look at first. You can add 1 to both sides and get 1 over x to the 2/3 equals 1. Not 11, but 1. And then the only way that's going to be 1 is if x to the 2/3 is 1, right? That's the only way this fraction can equal 1. You could also imagine cross-multiplying if you like. X to the 2/3 equals 1. The only way that happens, careful, is if x is plus or minus 1. Okay, so the critical points are at plus or minus 1. Negative 1, the cube root of negative 1 is negative 1. And then if you square that, you do get positive 1. The solutions are x equals plus or minus 1. It does turn out to be the case in this particular example that one of these critical points, negative 1, is not in the interior of the interval. It's at the endpoint, the left endpoint, in fact. But that's okay. We're just going to test those values anyway, those endpoints. So that's critical points, but we also have, as I mentioned a minute ago, a critical point where f prime of x is undefined. And that is 0. Here's where f prime of x equals 0, but also places where the derivative is undefined are critical points. F prime of 0 does not exist. So we actually have 3 critical points on this interval. One also happens to be the left endpoint. Let's now plug these numbers into the function. Don't forget to plug in 0. It is a critical point. And don't forget to plug in the right endpoint, 8, into the function. And again, it's a guarantee that one of these will be the global max value and one will be the global min value. F of negative 1, go back to the original function. Cube root of negative 1 is negative 1. Times 3 is negative 3. We're subtracting negative 1, so this becomes negative 2. F of 0, cube root of 0 is 0. 3 times 0 is 0. 0 minus 0 is 0. F of 0 is 0. F of 1, cube root of 1 is 1. Times 3 is 3. Minus 1 is positive 2. And f of 8, cube root of 8 is 2. Subtracting 8 there. 6 minus 8 is negative 2. The global min value occurred at 2 points. Negative 2 is the global min value. Also best lower bound. Best lower bound. But it occurs at 2 values of x. The left endpoint, which is also happens to be a critical point, and the right endpoint, which does not happen to be a critical point. The global min value, that's the global min value. What about the global max value? The biggest possible output here is positive 2. That's the global max value occurring at 1, the critical point in the interior of the interval. And best global max value is also called the best upper bound. Now, it'd be kind of tricky to graph this without technology. Let's just go ahead and use the technology right at the start here. I mean, it could be done. You could plot points and stuff like that, but it's something really subtle happens at x equals 0. So the function is 3 times the cube root of x, which is x to the 1/3 power, and then minus x. The window in question is -1 to 8. Global min value is -2. So let's go ahead and, okay, we'll put -3 here. And the global max value is +2. Let's see how this looks here. Yeah, something weird's going on at 0 there. You might look at that and wonder, why is that a critical point? Global max is at -2. Is a value of -2 occurring at x equals -1 and x equals +8. Global max is an output of 2 occurring at x equals 1. And yeah, the critical point at 0, and it is a critical point, is neither a global max nor a min, but you might look at that and say, why is that a critical point? It doesn't look like it's where there would even be a local max or min, and it also doesn't look like, in spite of my claim that it does not exist, it doesn't look like there's a corner in the graph. Well, there's no corner in the graph there, but it actually does have infinite slope. You could draw a tangent line at the origin there, but it would be a vertical tangent line, which has an undefined, or you might say infinite slope, and that means the derivative is undefined. But in this particular case, the global max or min value didn't happen to occur there anyway, but you do need to check it. If I'm going to graph this quickly by hand and also graph the best upper and lower bounds, we saw the graph looked about like this. There's -2 here and +2. If I draw horizontal lines up here and down here, those in effect represent the best upper bound, 2, best lower bound, -2. The function is always between those two values for all x in the interval from -1 to 8. And in fact, those are the best possibilities. Anything smaller than the best upper bound will no longer be an upper bound. Anything bigger than the best lower bound will no longer be a lower bound. Number 4 is a trig function example. F of x equals sine of x quantity squared. That's what that notation means. We sometimes say sine squared x, but we mean sine of x and then square it, minus cosine of x. The interval in question is the closed and bounded interval from 0 to pi. Do the same kinds of things. So let's find the derivative. Need to use the chain rule here. Sine of x is the inside function. The squaring function is the outside function. I bring down the 2. Sine of x to the first power times the derivative of sine of x, which is cosine of x. The derivative of minus cosine of x is plus sine x. Set this equal to 0. Solve for x. We can factor out a sine. And inside the parentheses, we're left with 2 cosine of x plus 1. These things are 0 at infinitely many values of x, but we're only concerned about the values of x that are between 0 and pi. Sine of x equaling 0 has solutions between 0 and pi that are 0 and pi. The endpoints of the interval are also critical points of the function. Pi is in radians. That's the same as 180 degrees. You can check this. Make sure you're assuming, when you're thinking about this problem, that x is in radians. 2 cos x plus 1 equaling 0 occurs when cosine of x is -1/2. Subtract 1 from both sides, then divide both sides by 2. For x between 0 and pi, 0 and 180 degrees, think about the unit circle definition of the cosine and sine. Cosine is the first coordinate of the point on the unit circle. It's 1 when x is 0. It's 0 when x is pi/2, which is 90 degrees. It has a first coordinate of -1/2 at the next special angle of 120 degrees, which is 2 pi/3 radians. And that is between 0 and pi. And pi, again, is 180 degrees. That's the only value of x in this interval for which cosine of x equals -1/2. So these 3 points put together are your critical points, and they are all in the interval, though again, the first 2 do also happen to be the left and right endpoints. All right, now let's check function values. F of 0 is sine squared 0, which means sine of 0, quantity squared, minus cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. This gives us -1. The critical point in the interior of the interval is 2 pi over 3. So I have sine squared 2 pi over 3 minus cosine of 2 pi over 3. Using memorized values, sine of 2 pi over 3 is square root of 3 over 2. We're squaring that. And cosine of 2 pi over 3, as we've already seen, is negative 1/2. So this becomes, when you square that, you get 3/4 plus 1/2, which is 2/4. And that gives us 5/4, or 1.25, for f of 2 pi over 3. F of pi, sine squared pi minus cos pi. 0 squared minus negative 1, careful with the signs, gives us positive 1. So the global max value is 5/4. That's the global max. Value, again, the word value emphasizes output. It occurs at x equals 2 pi over 3 in the interior. And the global min value is negative 1. And it occurs at x equals 0. Once again, the global max is the same as the best upper bound. The global min is the same as the best lower bound. What does the graph look like? Let's use blue here. Plot points. We are focused on the interval from 0 to pi here. F of 0 is negative 1. F of 2 pi over 3 is 1.25. It's negative 1 here. F of pi is back to positive 1. 2 pi over 3 would be around here, say. And so I guess the graph's got to look something about like that. Probably should confirm it with the calculator. Get rid of that one. Sine of x quantity squared. I'm going to use parentheses in a way that I want to make sure I don't make a mistake here. And then minus cosine of x. Window goes from 0 to pi. And the y direction, let's go from maybe negative 1.5 to positive 1.5. And let's make the tick marks. Sorry. Make the tick marks maybe 0.25 units apart. That'd be good to pick. Okay, it is concave up at first. Then it becomes concave down. And yeah, global max is there. 2 pi over 3. I don't know if that's what that tick mark is or not. It is 5/4, 1.25. Global min is negative 1 at x equals 0. As far as the x scale, let's go ahead and make this pi over 3 for the x scale just to confirm. That seems right. Pi divided by 3. 2 pi over 3 now is that point right there. And yeah, that looks pretty good. Okay. Let's finish the graph by hand. Looks about like this. Oops. And again, best upper bound 1.25, best lower bound is negative 1 for the values of x in this interval. One more pure math example before we do our application. I forgot to give the function name here. The function is f of x equals the quantity 10x minus x squared all to the 2/3 power. The interval is the closed and bounded interval from negative 1 to 8. 2/3 power. I wonder what, if anything funny might happen with this. The answer is yes. There is a critical point where the derivative is undefined. Don't forget the chain rule here. I will set this equal to 0 and solve for x, and those will give 1 or 2 critical points. But this is also undefined when this is 0 because, well, this is not really a proof, but it's a hint that this probably f prime of those points is undefined because you got a negative power here. This is the same as 2 times in parentheses 10 minus 2x all over 3 times in parentheses 10x minus x squared to the positive 1/3 power by definition of negative 1/3 power. So when we set this equal to 0, the only way it's 0 is when the numerator here is 0. 10 minus 2x equals 0. So 2x is 10 and x is 5. That is a critical point in the interval. But this is also got critical points whenever this thing is undefined, which means you'd be dividing by 0. Again, that's not a proof, but it's a plausibility argument. 10x minus x squared equals 0 can be factored as x times in parentheses 10 minus x equaling 0. This is 0 when x is 0 or 10. However, careful, 10 is not in the interval, so we can ignore it. So the critical points in the interval from -1 to 8, using interval notation, are x equals 0 and x equals 5, not x equals 10. And yes, 0 is a critical point, even though f prime of 0 is not 0 there. It's undefined. Again, this is no proof, but it is still true. All right, now test for global max and min values. That's not the final answer. F of -1 is f of the left endpoint. Plug in -1 up here. Get 10 times -1 minus -1 squared, all to the 2/3 power. That becomes a minus 10 minus another 1 is -11 to the 2/3 power. Let's just go ahead and approximate that here. Let me just double check that I did that right here. Yeah, it looks correct. -11 to the 2/3 power. Technically what you're doing is taking a cube root and then squaring it, so we will get a positive number here. I should have put the negative sign in parentheses here. -11 to the 2/3 power. About positive 4.946. Check this critical point. F of 0 is 10 times 0 minus 0 squared to the 2/3. That's 0. F of 5 is 10 times 5 minus 5 squared to the 2/3 power. So that's 50 minus 25 to the 2/3 power, which is 25. 25 to the 2/3 power. That's about 8.550 if you round correctly. And finally, f of the right endpoint, f of 8, is 10 times 8 minus 8 squared to the 2/3 power. That's 80 minus 64 is 16 to the 2/3 power. And that is going to be approximately 6.350 if you round it correctly. Okay, so what's the biggest and what's the smallest? There's your biggest, global max. And it occurs at x equals 5. There's your smallest, global min, and it occurs at x equals 0, which is the critical point where the function had a derivative that was undefined. And in this case, it's not an infinite slope. Let's just go ahead and use the technology to graph it right away. It's not an infinite slope at the point in question, at least not a two-sided infinite slope, you might say. Instead, there's a corner in the graph, or sometimes called a cusp. So the function, again, is 10x minus x squared all to the 2/3 power. Window in question is -1 to 8. Let's go, say, 0 to 10 for the y min and y max. Okay. Global min value is at 0, and its value is 0. The global min value itself is 0, and it occurs at x equals 0. The global max value occurs at x equals 5. 1, 2, 3, 4, 5. And its value is about 6.35, or 8.55, excuse me. Let's change the window a little bit just to confirm that. Let's make this 8.55 itself for the y max. Yeah, that looks pretty good. I won't draw it by hand, but if I drew a horizontal line up here, that'd be represent the best upper bound corresponding to the global max value. I should use the word values up here. And a horizontal line, that's the x-axis, would correspond to the best lower bound. And yes, there is a cusp in the graph at x equals 0, a corner in the graph. F prime of 0 is undefined. Our last problem is an application about inventory. A warehouse selling cement has to decide how often and in what quantities to reorder its cement. It is cheaper on average to place large orders because this reduces the ordering cost per unit. Okay, if you make large orders, the company you're ordering from probably won't charge you as much per pound of cement or something. On the other hand, larger orders mean higher storage costs. Maybe you got to buy a bigger warehouse or make more room. The warehouse always reorders cement in the same quantity Q. Doesn't say the units, that could be pounds or kilograms or whatever, or maybe thousands of such. The total weekly cost C of ordering the storage is given by this formula here. No function notation is given, but certainly this could be called f of Q. Q is the variable. Even though they order the same quantity, Q is going to be the variable because we are after the value ultimately of Q that gives the minimum total cost. A and B are positive constants, unspecified constants. Of course, we could give specific constants if we wanted to. Part A, which of the terms A over Q and B times Q in this sum represents the ordering cost and which represents the storage cost? All right, think about the description. The ordering cost is per unit is minimized or made smaller at least when the order is large, when Q is large. Which of these quantities gets smaller as Q gets larger? It's the fraction A over Q, where Q is in the bottom. That must be the ordering cost. Is the ordering cost because it gets smaller as Q gets bigger. Okay? Arguing for really, really, really big orders. But there's a competing factor. B times Q is the storage costs. These get larger. This gets larger as Q gets bigger or larger. And we're adding them. So intuitively, there's maybe some sort of middle ground, some sort of ideal value of Q that minimizes total cost, which is the sum of these two. And that's what we want to figure out in part B. What value of Q gives the minimum total cost? What's the domain of this function? Well, Q can't be negative. You are also actually ordering something, so Q can't be 0 either. Q must be strictly positive is the domain in interval notation. That's 0 to infinity, not including 0. It's not a closed and bounded interval anymore. We cannot plug in the endpoints here. We just need to find the derivative, set it equal to 0 to find the critical point or points. And maybe by the nature of this sum, we would convince ourselves that it has to be, in fact, not just a local minimum, but a global minimum. So what's the derivative? Q is the variable, A and B are constants. This is the same as A times Q to the negative 1. Alternatively, I could use the quotient rule. F prime of Q is the derivative of that, negative A Q to the negative 2, plus the derivative of B times Q, which is just B. Set that equal to 0 and solve for Q. It's the same as B equals positive A over Q squared, or if you cross multiply, Q squared is A over B. And so Q is plus or minus square root of A over B. But we want the positive one. Q is positive, so Q is positive square root of A over B, which is the same as the square root of A divided by the square root of B, and either answer is fine. That's the value of Q that gives the minimum total cost. Well, we haven't checked that it's a minimum, but it will be. That'll be the answer to part B. How could you check that it's a minimum? You could take the derivative. Well, think about the sign of the derivative and how it changes sign here. You could think about, technically speaking, the first derivative test. That would confirm you have a local minimum here And that local minimum would have to be a global minimum because it's going to turn out that the first derivative is negative over here and positive over here for all values of q. And that would really be enough to say it's more than a local minimum. It's actually a global minimum. We're not thinking about negative values of q. You can ignore those. F prime of a number in here. What's an example of a number in there? Well, take this thing and divide it by 2. For example, square root of a over 2 times square root of b. F prime should be negative. If you think about the formula for f prime, you maybe think of it as b minus a over q squared, or if you prefer by getting a common denominator of q squared, it would be b times q squared minus a over q squared. The bottom of that fraction is positive no matter what q is. But the top, if q is small, close to 0, this is going to be close to 0, and you're subtracting something that's bigger if q is close enough to 0. It's going to make it negative. F prime in this region is going to be negative, and f itself will be decreasing. You plug in a number bigger than that, a big value of q is going to be enough to make the numerator positive. Again, the denominator is always positive. So f prime of a number there is positive. Function, the derivative is continuous everywhere. F is definitely going to be decreasing when q is between 0 and this, and increasing afterwards. It will not only be a local minimum, it will also be a global minimum. And again, that's the answer. That's the value of q that gives the minimum total cost. If you plugged it into the original function, you could actually find that minimum total value. You could actually find the minimum value of the total cost.